All right. Hi, everyone, and thanks for coming back to the Soil Health Training Program webinar series. This is webinar 4, Soil Health Assessment Toolbox. Again, wanted to start off today thanking the Lake Champlain Basin Program and NUIPIC for the funding to create and host this Soil Health Training Program. And thanks to all of you for being here today. Today, we're going to go through the regular agenda. We're going to do a quick course overview, homework review, and then our presenter, Lindsey Ruhl, is going to present about the Soil Health Assessment Toolbox. And we will have questions and answers interspersed throughout the presentation. So have your thinking caps on, and then we'll go over the next class as well. So again, just to frame kind of where we are, we've had 3 webinars already, and those were in 2023. And now look at us all the way over here in 2024 with this presentation. And this will be the last part of part 1, which is what is soil health and how do we know if our soils are healthy? And so starting next week, we'll move into part 2, which is how do we manage for soil health? And we'll start that off with Heather Darby, who works with Lindsey. And we'll keep that running. Just a quick homework review. We read chapter 23 from Building Soils for Better Crops. It was called How Good Are Your Soils? And those are all of the different topics that were part of that chapter. Hope everybody got a chance to see that. And we're going to touch on many of those items today with Lindsey. And with that, I'm going to introduce Lindsey Ruhl. So for the last eight years, Lindsey has enjoyed working with UVM Extension Services, conducting agriculture research and water quality outreach. Before that, she earned a master's degree in plant and soil science from UVM and conducted cover crop research in Turkey with a Fulbright grant. With that, Lindsey, I think we're ready for you. Very excited for you. Please take it away. And again, as people have questions, please put them in the chat. Or if you want to come off mute during each Q&A, we can also arrange that. So with that, Lindsey, take it away.
All right, let's see if this will work here. We good to go, Lauren?
That looks great.
Excellent. Thank you. Well, thank you for that introduction. And it's good to be here today. It's good to kick off the new year with a hopefully fun webinar for you folks. So with that said, I do have a certain reputation to uphold, and I kind of alluded to that earlier, but I got to tell a couple of jokes before I really get started. So here are a few. What did one soil say to the other? We really need to stick together. If you didn't get that, it's an aggregate stability joke, and we'll touch on that later. All right, so here's another one. What did the soil say to the plant? I dig you. This is a good Valentine's Day joke. You can use this in next month. I think it's a little bit of the opposite, though. I think it's really like the plant's digging the soil with the little root going down there. All right, and this is the last one. I feel like I'm part of the millennial generation, so I'm going to go for this. Why did the soil go to therapy? Had some deep issues. All right, let's dive into this now. Lauren, you're the only person I can see, but you're laughing, so that feels good. Thanks.
They were excellent jokes, Lindsey, as always.
All right, and there we go. Okay, so today I'm here to give you a little bit of a brief overview on soil health tests and assessments. Testing our soil is important because it can give us information on what our plants might need to grow or help us identify areas for improvement. Soil health tests are one tool that often gives us values for specific indicators or confirm for us what we might already know or be experiencing in terms of our crops or soil health. And as Lauren said earlier, I have some breaks put in throughout some spots in the presentation for questions and answers. So in general, what I'm hoping to cover in this webinar, what I'm hoping you will get from this webinar is a more of a familiarity with some common tests, routine soil tests, soil health tests, and some visual assessments. Um, and then also, like, how do we interpret these tests? What do they mean? I was also asked to present a little bit on the back end, like how they're measured in the laboratory. And I'm gonna go say before I start this presentation as well that the soil tests that I present today I'm only presenting a few of the ones that are available, and by presenting them, I'm not necessarily endorsing any one over the other. I'm just going to share my experience with them. So with that in mind, I wanted to start with a little bit of context, and by acknowledging that our common soil test analysis are really heavily dependent on the measurements of the chemical indicators. This is in part because our scientific understanding and the tools, the equipment we have available are really geared towards that type of measurement. We can create standard operating procedures with standard extracts and get hopefully a consistent value. And so I found this image from Lehman and others, and I thought it was really interesting to kind of illustrate as an example how many types of soil tests rely on the chemical indicators. And you might have seen something like this, like the soil texture triangle, but this again is indicator types included in soil health assessment. So on this right-hand leg of the triangle, we have chemical indicators, on the bottom, physical indicators, and on the left, biological indicators. And you can see that not only the number of tests, but the number of indicators within a test really rely more on the chemical indicator part. We see a few on the physical and some on the biological. And that may be partially because we don't have as many instruments to test those indicators specifically. And then within the larger triangle, you can see there are these tinier triangles, yellow representing plant production, blue representing water quality, orange representing climate, and the green representing biodiversity. And again, a lot of those chemical indicators are really geared towards what's going to help our plant production, with fewer indicators on our soil health test for water quality, even less on climate, and even less on biodiversity. That's not to say that these other types aren't important. We just don't have the number of tests for those particular kinds of categories. All right, so here's two examples of routine soil tests. In Vermont, we use routine soil tests for our nutrient management plans to meet Vermont state standards. I want to get out ahead and say that these two soil tests in particular are not from the same field, so they're not comparable. But I wanted to use this as an example to illustrate that routine soil tests often have some of the same types of indicators or analyses on them. So I'm going to go through really quickly on what they have in common, and I want to dive into each one of those indicators and explain a little bit more about them, and then talk about some of the differences between the tests. So I'm just going to go through this pretty systematically. On the top of both of them, there's a couple number of indicators, and they are broken into these categories. Both of the tests have different nutrient analyses measured in parts per million. And then we also have pH on both the tests, so organic matter, cation exchange capacity. And I'm coming back to these categories because that's pretty much what they have in common in addition to the nutrient recommendations, but we'll get into that in a moment. One of the things I want to mention on these two routine soil tests is that they do measure the nutrients in parts per million, but one quick way that you can convert that if you're interested into an approximation of the pounds of that nutrient you have per acre in the top 6 inches is just to multiply that number by 2. So in the upper left here on University of Vermont's Agricultural and Environmental Testing Laboratory, our phosphorus amount is 6.4 parts per million. And so that would say approximately that there's 12.8 pounds per acre in the first 6 inches of your soil, assuming that that weighs 2 million pounds. So what we have here are these categories, and in UVM's Agricultural and Environmental Testing Lab and in the Dairy 1 lab, they break them into 5 different categories of very low, low, medium, high, and very high. In the case of the AETL lab, the agricultural and environmental testing lab, we have low, medium, optimum, high, and excessive. These categories, although named differently, should have the same points that they're broken off in. So when we're talking about these categories of low, medium, optimum, high, or excessive, that range, what it's really talking about is that these categories are based on the probability of crop response to nutrient additions. By crop response, we mean the potential that if you add nutrients to your field, the crop yield or crop quality will increase. So an example on the left in the AETL report, all nutrients are optimum or above, meaning that there is a low probability of crop response to addition of nutrients. Nutrients in the high category generally mean that more nutrients are present than are needed for optimizing yields. Except there is an exception, except for when it comes to potassium. Some crops are high demanding potassium crops, like alfalfa, and may need additional potassium in high yielding fields. So there may be some cases where potassium is in the high category for soil nutrient content for most crops, but not all. So please consult a crop advisor, NRCD, NRCS, extension staff, or the nutrient recommendation for field crops in Vermont guidebook if you need recommendations or want to learn more about these particular categories. You'll notice that the nutrient values found on the table are repeated below with an optimum values for comparison. If we can, there we go. So we have our phosphorus listed here, 6.4, and then below again 6.4, and it's saying this optimum range, this breakout, is between 4 and 7 parts per million. I think one thing to keep in mind when we're talking about this is that not every nutrient has an optimum range that is the same for every nutrient, right? So our phosphorus is 6.4 and it's in the optimum range, but our magnesium is in 116 parts per million. It's a little bit above the optimum. And when we look down here, we can see it's between 50 and 100. And that optimum range is based off of average crop nutrient need.
Hey, Lindsay,
Yes.
we have a question in the chat
Thank you.
confirming that these are theoretically plant available concentrations. Is that correct? Yes.
Theoretical. Yes. This is a really good question, and we'll touch a little bit on in one of our other soil tests, looking at the difference between the amount your soil has versus what is plant available. It's a really good, timely question. Any nutrients in the excess category may be an indicator that addition of nutrients may cause a nutrient imbalance. So adding nutrients when there aren't recommendations or your nutrients otherwise in the higher excessive category only aren't bad for your pocketbook, right? The bottom line, they're kind of waste if the soil has them and your plant doesn't need them, but it can also be detrimental to the environment. Okay, so if we look at the categories on the right here, whoops, go back here. Potassium is just barely above the very low category right here. This indicates that it has a high to moderate probability of crop response. If you add potassium, most likely your crop will increase in yield or quality. And to wrap up this particular slide, the other thing I wanted to draw attention to is that both of these tests indicate what kind of extract they used, and both of them use modified Morgans. And part of the reason why they use modified Morgans is because these are Vermont soil tests, and to meet Vermont state nutrient management planning standards, your soil tests have to be, or your soil needs to be extracted using modified Morgans. But just to talk a little bit about that, I think it's really important to stress that different nutrient extracts mean that there are different methods, and because of that, they are going to yield different results. So in the addition to modified Morgan tests, there's also Morgans, Malik 3, Bray, and Olson. We use modified Morgans in Vermont for a couple of reasons. One is that before modified Morgans, there was the Morgans test, and that Morgans test was created specifically for New England growing conditions. Later in the 1960s, it was modified to better be able to extract potassium from the soil. But with that, how I've come to think and learn about modified morgangs has been a lot through the lens of phosphorus. And part of that's because that's the nutrient of concern in Vermont. And so I wanted to draw attention to this little, Pac-Man chain, I guess, if you will, for phosphorus extraction ability, just to kind of put some context for these different types of extract. So malic 3 is, in the literature I was reading, is the most aggressive, they use the word aggressive, extract to get phosphorus from the soil to measure it, followed by Bray, which is less aggressive, and then Olson and modified morgans, less aggressive than Bray's, but more aggressive than the morgans. So there's some of that context there. Oh, we use modified morgans. I added that little animation and forgot to click before I said it, but there it is in green. Okay. Kind of driving home this point of that using different extracts will yield different results is also that they're not necessarily convertible. So like if you get a test through malic 3, this is what this graph is indicating in the left, or this figure, that if you use malic 3, you can't like necessarily put it through some algorithm and spit out like what that would equal in Morgan's extract, and vice versa. So they're just not comparable in that sense. And then in this table too, I wanted to also illustrate and drive home a point that Fred made a couple webinars ago, basically indicating and reinforcing the importance of going to the same lab year after year after year. So even though, in science, right, like if you use a different extract, you can expect a different result. But ideally, if everybody's using the same standard operating procedure and the same extract in a lab, you should be getting the same result no matter where you go. But according to this fact sheet from Cornell, fact sheet number 15, when they sent these 4 different samples, soil samples, out to these 5 different labs, they ended up getting different results from each of the labs for these soil samples. So that might range between a couple parts per million, not a big deal, but for some, especially for phosphorus, and if you're making a nutrient management plan, like those phosphorus results do matter, they can range as much as by 20 parts per million. So it's really important to, if you find a lab that you like, stick with it unless you have a reason not to. I think that's all I have to say about that. And I can't help but go into this too, because I'm about to talk about lab procedures, but before we talk about lab procedures, just analyzing the soil sample you took, we should probably talk about taking a soil sample. So where are you when you're taking a soil sample for your agricultural fields? You're in the agricultural field, right? And so when you're in there, it's really important to take a representative soil sample. And by representative, I don't mean one, actually, I mean 15 to 20 in a field that is 20 acres. So in this example here, we've got a field that's over 20 acres. So that should really be broken into 2 different sections. And the research shows that the ideal number of soil samples to get for a 20-acre field is between 15 and 20, which is what the recommendations are that are given through our nutrient management planning course. And the reason for that is that soil samples, any number of soil samples taken below 15, then your average that you're getting for that field is below the average, is not near the average. And then any samples that you're taking over 20, you're not really improving your chances of getting an average result. And when you're out there in the field taking your soil sample, you also want to take it from the spots that are most representative. So not necessarily the best, concentrating on all your samples in the best part of your field, and definitely not going towards the worst. Like that area that gets ponded year after year after year, that is not representative of your 20-acre field. So when you go out there, right, you got your probe and you get your bucket, and you're taking 15 to 20 samples. And depending if you're in a hay field, you're going 6 inches. If you're going to cornfield or some other annual till, you might go more like 12 inches. And then this is what you got in your bucket. So you're going from 20-acre field. You can't see my arms. My arms are like really outstretched. But you're going from a 20-acre field to some amount like this, right? And then I don't have a picture of this, but then you put it in a little bag. So you go from like maybe 8 cups to 1.5 cups, right? That's what you submit to the lab. And then the lab dries it, grinds it, and takes 4 grams of that entire soil sample that you submitted that's supposed to represent 20-acre field into their machine for analysis. And so this is a picture that I took with 4 grams of ground up soil next to 20 grams of ground up soil next to a Sharpie for comparison, right? So it's not that much. So it's really important, getting on my soapbox here, I'm gonna get off my soapbox on this particular subject in a second, to take a really good representative sample when you're out in the field. Okay, I'm moving on, we're going to lab analyses for this. And this is something I also really like to talk about. So when I was getting my master's, I ran a lot of soil samples through this machine, and I thought it was so cool. Probably not going to convey how cool I thought it was at the time to you now, but I'm going to do my best. So you submit your soil sample to the lab, they're going to grind it down to something like 2 millimeters, and then they weigh out that 4 grams. And then they put in an extract, the modified Morgans, they shake it up, and then that gets put from that container through like these little funnel containers with a filter to filter out the soil, get the extract. The extract then gets thread through this ICP, the inductively coupled mass spectrometer. And this thing burns insanely hot. It uses argon to feed this flame. You can't see it very well, but this little green thing here is a flame. And so basically this works like spectrometry. Like the general concept of this is that every element emits like a characteristic wavelength. And so phosphorus looks like this. Anytime the machine sees this wavelength, it's going to say phosphorus is there. And then the more of those there is, the higher the concentration is. So you've got phosphorus here, you might have potassium like this, and that's how it measures. If you've ever sent any samples for forage quality analysis, it doesn't get run through this machine, it gets run through an infrared spectrometer. But it's the same idea. There are characteristic wavelengths for particular elements, and that's how they're able to read the nutrients in a soil or a forage. All right. Oh, now I have a break slide. So, there are any questions, Lauren?
Thanks, Lindsay. There aren't right now in the chat. But I was wondering if you could speak a little bit more to out in the field for different crop types, getting different depths for your soil samples.
Yeah. So my understanding of that, I know we've all seen those pictures of perennial forage, right? And it's like those root masses are like 3 feet deep. And we know that grasses can scavenge nutrients below. But I've also experienced in the field and perennial fields in Vermont that concentration of the root mass sometimes tends to be in that first 6 inches. And so because that's where the bulk of the root mass is, that's the area that we're going to sample from, because that's where the bulk of the nutrients may be depleted and would need to be replenished. And I also know I've been out there in the cornfield, and like when you pull a corn plant up, it's like all like this big. But I think part of that too is that those are the depths that our recommendations are based off of as well.
We've got a question that the UVM soil test sheet says that the sample perennial for sample perennial vegetation 4 to 6 inches deep. Do you know if that's right?
Yes, they are correct.
Okay. Wonderful. Keep the questions coming too, folks. I have one more for you though, Lindsay.
Okay.
The 15 to 20 samples in a 20-acre field, and if it's more than 20 acres, you should like split it in 2. But then you average them after for the NMP. And I'm wondering if you can speak to that a little bit, and if it's fine if you can't.
No. I also share, I'm like, how does that make from a practical perspective, you're like, how does that make any sense? But I think, you know, really that's where we're trying to marry the science with like the practical, right? Because I think what we want to see is how similar are they? Does it make sense to treat them any differently? Probably not if they are the same soil type and they've been managed the same for 20 years. But it's good to have those results to justify that. And I think the practical, so there's that's the science part, right? We know that about the soil sampling, but the practical part is that most farmers we're working with, if that's the field and they produces the same and the same crops on, and they've been managing it the same for years, they're not going to change that without good reason. But if we have the soil test results, we can make an informed choice from there.
Awesome, thank you. We do have another question from Dean. I'm kind of surprised by the amount of variation in results within a field as shown in the example. Are there reliable, observable characteristics found at each location that can explain the variation, or is it mostly just the nutrient that is different from spot to spot?
I think I need a little clarification of which thing that this question is being referred to. Is this referring to the table that I showed?
And Dean, if
where
you
the-
want to unmute, feel free.
Hi, Lauren. Yeah, it was the slide showing the field with the several locations where tests were taken and there was quite a range in results. Yeah, right there on the left. Oh, right there.
This one?
Nope, nope, the map, the overhead, right there.
Oh, so sorry, I didn't explain this map very well. The numbers up here, like the 8, 9, 10, 6, are the names of the field. It's field 8, field 9. These 11.95, 12.38 are the acres. This is not, these are not phosphorus results at all.
Never mind.
These are different fields. My apologies on that.
So
You're good, Dean.
You've taken the 20 samples within field 6. I guess what I'm trying to get a handle on is what would the range in those values be? Somebody's done somebody did a math.
Oh,
and
yes. So like you take 20 samples and each one of like those, like that probe, getting that analyzed.
Yeah,
So when I was talking about like taking 15 to 20 soil samples in that context, years ago, I saw a graduate student give a presentation where they did just that, where they took, they geolocated every soil sample they took and then analyzed that one soil sample to kind of figure out, well, what is the average and how many do you need to take to get to that average? But I don't have that person's information or probably the resulting paper that they created. I almost spent some time to find it because I was like, I'm kind of curious, but then I got distracted doing other things, but it's a good question.
thanks.
Mm-hmm.
All right. So, Lindsay, it doesn't look like there's any more questions coming in right now, but folks, there will be many more breaks and chances for questions, so we'll let Lindsay keep rolling.
All right. Okay, guys, put your seatbelts on or don't. I'm not here to judge, but we're gonna talk about the cation exchange capacity. Hope you're ready. So I think that this has been something that's come up a bunch and people might still have questions on, so I'm gonna lean into this a little bit. And I think Heather will also talk about this next week in her webinar. So the cation exchange capacity measures the number of positive ions. So cation exchange capacity is measured in milliequivalents, I might not be saying that correctly, per 100 grams of soil. A milliequivalent is the number of ions, it's a positively charged atom, which total a specific quantity of electrical charges. So the cation exchange capacity determines how many cations can be bound to the soil. The key word is exchangeable here. Cations can be replaced with each other. Cations are positive elements like calcium, magnesium, potassium, sodium, ammonium, aluminum, and iron. And so as this image illustrates, there are some soil texture classes that have a higher capacity for a higher cation exchange capacity. So as Fred was talking about, right, like clay, like all our soil has some amount of negative charge, but some soil textures have higher number of those negative charges than others. And so what this illustration shows is that clay has a higher number of those negative charges which means that it has a higher capacity to hold on to positive charges. It's like magnet situation, negative, positive sticking together. So the clay has more of those negative charges than, for example, a sand. I think a question that had come up earlier that I wanted to address, and I kind of just listed a bunch of them here, are a list of different types of nutrients, and there are forms of them that are cations and also anions. So for example, nitrogen is available at the cation, so something that can stick a little bit more easily to those negative charges on the cation exchange capacity as ammonium, but it's also present in the soil as an anion, as nitrate, which means that it doesn't stick to the soil as easily, which means that it can be lost through leaching. So one thing I think is kind of interesting to contextualize this a little bit more when we're talking about cation exchange capacity and potential to think about that in terms of pounds of nutrient or element per acre. We can look at it in this way, if that for every 1 milliequivalent of calcium that you have in your soil test report, that means you might have 400 pounds per acre of calcium. But note that different types of elements have different weights to them, which means that they're going to have, if you're multiplying their weight by the amount that they are in the cation exchange capacity, means that they will have a different number of pounds per acre available. So 1 milliequivalent of calcium, about 400 pounds per acre, 1 milliequivalent of magnesium, about 240 pounds per acre. The other thing that I think is really interesting and to keep in mind, because there is a little bit of this relationship between cation exchange capacity and pH, and that is because not only are there cations that have a basic effect, like an alkalizing effect, there are also cations, this blows my mind, that can be acidifying, right? So I'm like, cations, positive charge, but somewhere in the magical chemical world of soil, there are some cations that impact pH, that acidify the soil. Sodium, aluminum, and hydrogen. Just make sure I hit everything here.
Lindsay, if you are done on this slide, there are a couple questions.
Oh man, can we hold on a moment on this one?
Yes.
I wonder if I might answer some questions. I might get some more with the next slide. I think I've got one more slide on cation exchange capacity.
Sounds great.
Okay, so cation exchange capacity is estimated, there's a notable point here, it's estimated at a projected pH, which varies depending on the crop to be grown. Different crops prefer different pHs. So on your soil test from the AETL, the projected pH or pH management level is explicitly stated for your crop in the laboratory results sections or in your recommendations. Because of this variation in nutrient holding capacity, a single soil can have 2 entirely different cation exchange capacity estimates if recommendations are requested for 2 crops with different optimum pH levels. So I think one of the things that's driving home that point that cation exchange capacity is dependent a little bit on that physical soil properties of the texture, the percent sand, silt, and clay. When we look down here on the on this graph from the Brady and Weil textbook, again, just kind of at that same image that we were looking at previously, sands, loams, silts have a lower cation exchange capacity than clay loams, which all have a lower cation exchange capacity than finished compost, which all has a lower cation exchange capacity than soil humus. I think this kind of goes along with some of the webinars that we've heard previously and just thinking about that number of negative charges. And this is just a table to kind of reinforce that same thing, but with a little bit more of some of the hardline values on the right here. So your sands, lower milliequivalents, lower cation exchange capacity than your loams and silt loams, and your dark colored loams and silty clays and your organic soils. Okay. thank you for letting me get through that one other slide. I'll try to answer questions on cation exchange capacity.
So I'm gonna go with Mel's question. So on the last slide, if nitrogen is more likely to leach in its anion form, what happens to phosphorus? Because the table indicates that it exists as an anion, not a cation. But we know that phosphorus doesn't really leach.
Yeah. And this leads into also talking about recommendations, which we'll touch on in a moment. But so you've got your cation exchange capacity with all those negative charges. But there's other minerals in your soil, and one of those or other elements, and one of the other elements are elements that have positive charges like iron and aluminum, and those bind to phosphorus. So that's how phosphorus can become a little bit more immobile, is when it's binding to some of those other elements.
So I think this leads into perfectly for Peter's question. A number of farmers I talk to say calcium is very important for phosphorus uptake. Do you think you could speak to that as well?
No, I can't speak to that. I'm not familiar with that. I'm not saying that that's not happening or isn't important. It's just not something I'm familiar with. And I'm wondering if that has anything to do with a liming effect, if like they're talking about putting calcium carbonate down and like how changing the pH might change that, and that could be related. And that's actually the next section, because cation exchange capacity and pH is related in that sense.
Yeah, calcium carbonate. That's true. That's specifically, yes.
Okay. Just
Sorry.
wait a couple more minutes and we'll have some pictures that will hopefully help answer that question.
Thank you.
Yeah.
Wonderful. Thanks, Lindsay. Those are all the questions in the chat right now.
Okay. Well, thank you. Yeah, keep them coming. This is great. pH. Here we are. This is where you find it on these respective soil tests. Man, I gotta tell you, explaining pH really can get tangled up in my mind. And then when I was putting this presentation together, how it was laid out in one of the sources I looked at, helped it make a lot more sense to me. So pH can be understood as the power, the P, of hydrogen. And what confuses me about this is that how I typically see hydrogen presented is with a plus. And I'm like, well, how can the more hydrogen, something that has a positive charge, make something more acidic? Because you add calcium carbonate, which is something with a positive charge, to reduce the alkalinity. So I was really confused by this, and I hope that my confusion in sharing that can just make you confused. But that's why I started thinking about it in this way. So hydrogen is positively charged, but when we're talking about that, we're talking about the ion form of it. So, but if we're talking about the hydrogen atom, it has one positively charged subatomic particle, a proton. It has one negatively charged subatomic particle, an electron. We're like going back to like high school chemistry if you've taken that. But when the hydrogen atom gives up its electron, its negative charge, it becomes a positive ion, hydrogen plus. So pH is measuring the amount or the power of those negative electrons. So, and also I think it's important to say that when we're measuring pH, when you get that result in your soil test, it's measuring the amount of hydrogen in your soil solution, not what's stuck onto your soil, not the cation exchange capacity, what's in the soil solution, what's in the water in your soil. So for these reasons, pH and cation exchange capacity really heavily influence to some degree nutrient availability. We'll touch on that in a minute, but I want to just talk about these illustrations for a moment here. So in general, right, like I was going to say, humans are much like plants. I mean, there's a lot of differences, but when we're talking about pH and like where we feel as organisms the most comfortable, it's in this nutrient neutral area, right? Water, pretty easy for us to deal with. We got blood in our bodies. I mean, we also have stomach acid, but that's pretty corrosive stuff too. And milk. All these things are in the neutral category. We get along pretty well, but anything that's more on the acidic side or more on the alkaline side can become toxic or otherwise abrasive. So plants are kind of similar in that sense too, is that most plants thrive the most at a pH of 6.2 to 7. And then there are some plants that thrive more in an alkaline soil, like our alfalfas, or more in an acidic soil, like our blueberries. And part of the reason why that is because at these different pHs, their nutrient availability can change. And when we're looking at those big three, those big macronutrients, those nutrients that our plants need more than others, the nitrogen, phosphorus, and potassium, they're more available in that neutral category and less available when our soils are more acidic or more basic. Some nutrients do become more available when the soil is more acidic, and that can cause some issues for our crop quality as well. So one good way to fertilize your field oh, I just saw my camera went bad. Hold on a second here. See if I fixed it. Nope, we're not coming back. Hold on a moment. Okay, there we go. Thank you for your patience.
Beautiful.
So one cheap way to fertilize your field if your pH is off is to lime it, because that will increase the availability of nitrogen, phosphorus, and potassium. So also not shown on this particular illustration is aluminum, which is more available when soil is acidic. And the more aluminum there is, the higher the potential there is to bind or tie up with nutrients like phosphorus, which can make it unavailable to plants. Sorry, there we go. All right, pH and lime. So let's chat about this for a moment. Or what happens to your pH when you lime? How does liming affect pH? So let's look at this illustration. On the left-hand side, we can see there's a bunch of hydrogen. So we got a lower pH, more hydrogen. Got some aluminum hanging out, and we got a calcium as well. Now, when we add lime or calcium carbonate, what's happening is that calcium addition is getting incorporated into the soil, and it's knocking that hydrogen out. It's taking on that area where the hydrogen was, right? Because hydrogen's clinging on with its +1 charge. Calcium's got a +1 or more charge. And so it's able to displace that hydrogen, replacing it with calcium. And the hydrogen, remember, it's a cation that has an acidifying effect. So when you remove the hydrogen, you're increasing the pH. You're decreasing the acidity. And so when you're adding calcium, the byproducts are water. That's where the hydrogen goes. It goes out as your water. And then the carbon also gets displaced. And so what's happening in this process is that when the hydrogen ions in the soil solution are neutralized by the lime, the hydrogen ions from the soil surfaces are released into the soil solution to maintain that equilibrium and resist increase to pH. Clays are generally better buffered than loams because they have more of those negative charges. I'll put that up there. Which in turns are better buffered than the sands, right? So that basically when I'm talking about them being buffered, what I'm talking about is that in this example, for example, for every 1 ton per hectare of calcium carbonate that was added to sand, they saw a pH change of 0.5 to 0.7. Because remember, sand doesn't have as many negative charges. So you need to add a little bit more to achieve a similar pH change in a soil like a clay that has more of those negative charges, is holding onto the hydrogen a little bit more. So for 1 ton per hectare of calcium carbonate added, there's only 0.2 to 0.3. And I do just want to cite my source here for that what I read about when hydrogen ions are in the soil solution are neutralized by lime. That I grabbed from the Government of Western Australia website, but that was like one of the easiest ways I saw to explain that. And I'm going to just talk a little bit more about pH and nutrient availability before we move on to something else, and then we can take questions too on this piece. So I think one thing that I just talked about, right, is that pH impacts nutrient availability. And I think there's something to be said about that with hydrogen, but there's also something to be said about that our bacterial populations prefer a more neutral pH. And if they prefer that, they're going to be working more in that neutral pH than in either something that's more acidic or more alkaline. And so what we have here, this is from a paper by Rusk et al., And on our top picture here, we've got bacterial populations and fungal populations and pH on the bottom. And you can see that as pH increases, as the soil becomes more alkaline or less acidic, our bacterial populations increase, but our fungus doesn't. So this is pretty interesting that our fungal populations stay a little bit more stable as pH changes. And I think just I'll put some context of why this is important is that when our pH is optimal and our microbial populations can thus be at their optimal state as well, they have a higher likelihood of recycling those nutrients. And I think it was Lisa Blaser, I might not be saying her last name correctly, but she also had this in her presentation, right? That like very little fertilizer that is applied gets taken up directly by the plant. And so it's great to have a microbial population that's going to take as much of that in and cycle that through the system for when your plant is able to take it up. So that's why maintaining bacterial populations, or one reason why maintaining bacterial populations is important. This paper also had this other picture, and it's a similar concept, pH at the bottom, but what they're talking about, what this is illustrating now is the diversity. And what we see is that not only do the bacterial populations increase, but their diversity increases with increasing pH, but the fungal populations stay relatively constant. There are a bunch of different ways to measure pH. This is the one that I'm most familiar with and what the lab probably uses. Put your soil solution in some water, you have an instrument that measures it. You can also measure pH directly in the field with a probe-like instrument like this. And there's also, again, a water solution that you can put your soil into, let it sit, shake it for a little bit, and then let it sit, and then you can use a filter strip. And question time.
Awesome. Thank you so much, Lindsay. We've got a comment here from Willie, and Willie, feel free to come off mute and talk a little bit more once I read it. But that CEC is one reason to have soil texture analysis on all fields, which needs to be done only once, as it will not change unless the top soil is completely stripped away or gravel is extracted, etc. Willie, if you want to speak any more to that, you are welcome to.
I don't know. I think it's pretty clear. It's not something that's emphasized though, unfortunately, within the agronomic realm. I don't feel some soil labs will put it on there as an option, make it fairly affordable, and other ones don't even make it an option really. You have to kind of dig around and see if you can have that done at certain labs. And I think but it matters a great deal, as Lindsay had already pointed out. Your CEC is going to only be able to have a certain capacity depending on the soil texture. So if you have a truly high sandy soil, your CEC is only going to be able to get so high. It's just, there's only so many negative charges in the soil that can grab onto those cations, and even if you add a lot of organic matter. So it is important, I think. It's just one of those baseline measurements that isn't talked about much, but everybody should know what their soil texture is for each field. And again, it only needs to be done once, typically. Once in a lifetime. I mean, you don't, not once a year, once in a lifetime. So if you know it, you know it.
Thank you, Willie.
Yeah, well, I think that's a really great point, and that's something that I think I've been in conversation with like Lauren and other farmers recently too, was just thinking a lot about soil texture as an inherent soil property and what that means for sometimes the limitations and challenges you might have on that field, regardless of the management that you're using.
Yeah, to me, it's like, it makes, I mean, if people haven't really gone through like the soil survey for their own farm, it's really important to read those soil survey descriptions. And they may not be perfect, but they're pretty good and they're pretty helpful. And they essentially do this. They describe the soil texture, the amount of rockiness, the slopes. I mean, just these physical characteristics, you know, that are just important to kind of get your head wrapped around. And then when you walk out there, you're like, yeah, I feel it, I smell it, I get it, I look at it, you know, so yeah.
Thanks,
Yeah, and
Willie.
I can't help but add to Willie to that, the depth to water table or seasonal water
There you
table
go.
depth. That
Right.
is so important when you're thinking
Absolutely.
about what crops you can establish that will thrive in that particular field. And again, that's in general, regardless of your management practices.
Oh yeah, yeah. You're not going to
Geological
change that,
feature.
right? That's so good.
Lindsay, I'm going to ask you a question, but first, can you go back to the bacterial and fungi populations versus pH chart and just leave those up while I ask a different question?
Mhm.
Thank you. Got a question from Mel. Are there generally difficulties with balancing crop needs for macronutrients and micronutrients when liming because some of the micronutrients are more available in acidic soils? Or is it usually not a problem because micronutrients aren't as important?
Oh, no, every nutrient is important, but not all nutrients are needed in the same quantities. Well, I do have another slide that's a little bit on this. So can we put a pin on nutrients deficiencies and needs? But I think part of the question is, Mel, can we sit on that for a moment?
Yes, we can.
Oh, okay, thank you.
And then I just wanted to point out for folks, there are a couple of videos that Charlotta is putting in the chat. We will copy and paste those as resources on the campus page as well. Just so you all know. And then she also mentioned it's important to remember that organic matter plays a huge role in CEC and is not a part of your texture analysis as well.
Yes.
And
Really
then
good points, thank you.
one other, I guess I was just wondering if you could repeat your confusion and then unconfusion around pH, because I got a little confused listening to your confusion and think some other folks might have too.
Okay, so here was my thought. I don't even know if I should do this because this might be more confusing. So pH measures the more acidic your soil is, like the lower the pH is, right? So you got a lower pH, but that's measuring the amount of hydrogen. That's what pH measures. And so how I've typically seen hydrogen written is H+. And so one of the things I didn't understand is that some cations, something with a positive charge, can actually have an acidifying effect. And so that's why I was confused, because I was like, you add calcium carbonate, that has a positive charge, and that increases pH. So what I had thought, not thinking more, like not knowing more, was that anything you add with a positive charge would, increase the pH, when that's not true. But I never dove deeper into it because my realm was like nutrient management planning. I was like, I don't need to know that, and moved on. So that's where my confusion was.
Thank you. And then you also mentioned, you emphasized pH is measuring the soil solution, not what's connected to the particles. And I was wondering if you could re-emphasize that before you move on, because that feels important.
I think part of why I wanted to emphasize that was to draw a distinction between cation exchange capacity, which measures all cations, which does include hydrogen, but that's what's connected to the soil, versus pH, which is just measuring hydrogen in the soil solution.
Perfect. Thank you very much. No other
I
questions
can answer
here.
that a little bit
Oh.
too, if that's okay.
No, please
Yeah,
do.
please do.
So I always get a little annoyed when I see the soil samples come back because they use often distilled water to measure your pH in the soil. And that's going to actually give you even less of the correct pH because it's getting diluted compared to what it would be in the soil. So remember, as soon as you remove hydrogen ions from the soil solution, those that you were just talking about are going to come off of the clay or the organic matter. And then your pH is going to basically just equilibrate itself. So I think that's important to think about, that there's this hidden world of cation exchange that you can't see in that pH that you get when you send in a soil sample. I always think that people should do their own pH, and you should add potassium chloride to it, because that's going to pull off all your hydrogen ions and you'll be able to see the actual pH of your soil. So if you want to play with soil and water, do it yourself.
Thanks, Charlotta. And then Lindsay, I know I just said we can move on, but I've actually got one more thing for you.
Okay.
With what's on the screen right now, I know I've heard soils that are more acidic support fungal dominated populations versus soils that are more basic support bacterial. And so that does seem to be what it's showing, but it's interesting that the fungal is actually pretty flat. And so it's really, I guess what I'm interpreting is like the bacteria is really influenced by pH and fungal maybe less so.
That's what I would draw from that too. And I think the key word, and I've heard this too, dominated, right? So like it's that ratio that's changing.
Gotcha. Wonderful. Yeah, because I guess if you look at the y-axes on the first set of graphs, bacterial is kind of dominated anyway, no matter what. But it is interesting to think about. Thank you. We'll let you keep going.
All right. All right, where are we here? Oh, okay. We're moving on to a different set. We're gonna talk about organic matter, and I'm not gonna talk too much about organic matter because I think Fred spent a wonderful amount of time and presented a lot of different things on organic matter, and I can't recap them as well as he presented them at all. But I will say this that he said, which is that there's pretty much no other soil health indicator that isn't touched by organic matter except for texture. So we're gonna wrap that up. But I will talk a little bit about how it's measured in the lab. So when you send your soil sample into the lab, they do the same thing before it gets processed for organic matter, pH, and your nutrient availability and cation exchange capacity, right? They dry it, they grind it up, they put it through this 2mm sieve because we want to make sure that all the particles are of similar size. And then they're going to weigh out a portion of that soil. And then they're going to take that weighed soil that's in this little crucible and they're going to burn it at like 700 degrees. And the amount that gets burnt is the organic fraction. The amount that stays is the mineral fraction. So after they take it out of the furnace, they of course let it cool and then it goes back into a scale to measure. And so that difference then between what you started with and what you ended with is the amount of organic matter, and you divide that by what you started with. Your percent organic matter is right there. So now I'm going to just spend a little bit of time on the Dairy 1 analysis in particular, because they have a couple of things on here that the UVM AETL lab does not have. And one of them is exchangeable acidity. And just briefly, what this is it refers to the amount of acid cations. We just talked about this a little bit. That's aluminum and hydrogen that is occupied on the cation exchange capacity. When the cation exchange capacity of a soil is high, but has low base saturation, the soil becomes more resistant to pH changes. As a result, it will require larger additions of lime to neutralize the acidity. This, along with optimal pH for crop growth, determines how much limestone might be required to neutralize the acidity. Another thing that's on the routine soil test for Dairy 1 is soluble salts. This isn't something that was included in this analysis or is really included in the UVM AETL analysis because in general, in Vermont, we don't have issues with static soils, salty soils that could interfere with crop growth. So the Dairy 1 also has some base saturation, and let's just talk a little bit about what that is. Base saturation is calculated as the percentage of cation exchange capacity occupied by base cations. We've got those acidifying cations and we got base cations. Soils with high percent base saturation have a higher pH. Therefore, they are more buffered against acid cations from plant roots and soil processes that acidify the soil. So let's take a little bit of a closer look at this. Really lean into cation exchange capacity here. So on this image on the left, we have a soil with low cation exchange capacity, right? It's got 4 negative charges. And the example on the right of this illustration, we've got a soil with, I think, 8 sites. So a higher cation exchange capacity, twice as high as the low cation exchange capacity. And here, you know, got two different cation exchange capacities going on. And a couple of sites on our low cation exchange capacity occupied by an acidic or an acidifying cation, the aluminum and the hydrogen, and only one in the high cation exchange capacity. So I think it's a little bit more helpful to think about this base saturation and cation exchange capacity in terms when we're looking at two examples of high cation exchange capacity. So here in this illustration on the right, they both have high cation exchange capacity. This example, 8 negative charges, but our low base saturation here with a high CEC is because we have more sites occupied by the acid cations, whereas in our example on the right is dominated by the base cation, so it's a high base saturation. So that's base saturation and cation exchange capacity in a nutshell. Just wanted to explain that part of the Dairy 1 soil health or soil test. All right, and now I'm going to talk a little bit about what they both don't have. And the big screamy thing that they don't have are nitrogen results. Nitrogen is a particularly finicky nutrient, right? We saw that slide where it's available as a cation and an anion, so it can be lost to the soil in a couple of different ways, through water, by leaching, through the atmosphere, through volatilization. And because nitrogen levels can fluctuate so much, not only with management methods, but just with climate and what's going on, it's very temperamental, depending on how much rain we get, depending on the temperature, depending on what's been applied. The nitrogen recommendations in general are not based off of soil test results, but average crop uptake. So that's depending on your anticipated yield, what crop you're growing, and the soil drainage class. And when we're making a recommendation for nitrogen, we also take into account past year manure applications and also any credits from sod plow down. If you do want to measure the nitrogen in your soil, you can get a separate test. It's called a nitrate test. Often we take soil samples in late June, early July for a pre-side dress nitrate test, a PSNT test. And Fred didn't mention this, but I'm gonna say it, is he's the guy that came up with this, and he had the opportunity to call it like the Magdalf test, and he was like, nah, I don't want my name attached to it. But you can thank Fred for the PSNT test and saving you money everywhere for nitrogen, or maybe justifying applying more nitrogen and getting a better yield. So anyway, the PSNT test is typically used for mid-season corn recommendations, and I just want to take a moment to look at what that test looks like, or result might look like for that. You have a sample name. This is pulled from one of our trials, but your sample name might be like field 1, Mary's over yonder, or whatever. And then to the left of that, you have the nitrate level, the actual physical test result. To the left of that, there's a lab number. That's something the lab makes. You don't need to worry about that. And then here's how we read it, right? Is that there are these different categories for potential yield in either bushels per acre or tons per acre for corn silage, bushel per acres for grain corn. And in typical 15, 20, or 25 tons per acre segments, or 90, 120, 150 ranges for grain corn. And based off of the results, you get these different values. And you, as a producer or farmer or crop consultant, working with your farmer, knowing the field, knowing what it averagely produces, you would choose one of those items in the column as a recommendation. And there are some fields that under great management could go from 20 to 25 tons. And then there are other farmers that I work with, and they're like, no matter what I do to that field, just because of the soil type and where it's at, it's only ever going to get 15 tons, right? So some of this is a conversation between what can the field produce, what is the field producing, and what can it actually produce, and are they the same? I'm going to pause here for some questions.
Thanks, Lindsay. I've got a question from Tom. What's the difference between pH and buffer pH in the Dairy 1 test results?
You know, I don't know. And I will say I emailed Dairy 1 and I called Dairy 1 because like, I don't understand this. And they didn't get back to me. But maybe we can crowdsource this. I don't know if somebody else has an answer for that here.
Yeah, anybody think they have a thought? And if not, Lindsay, if you do get a response, we can also bring that into a future webinar. Not seeing anyone with an answer.
Oh,
So
but
we'll
did I
all just
answer
lay in
Mel's
wait.
question? No, I didn't answer Mel's question. We're gonna get to that soon. Sorry about nutrient importance.
Yes. And there's no other questions right now. So if you want to keep rolling, keep rolling.
All right, awesome. All right, let's talk about recommendations for a moment. I'm gonna breeze through this pretty quick. They both have nutrient recommendations. The lime recommendation is based off pH and crop grown. The nitrogen recommendation is based off the crop, anticipated yield, and drainage class of soil. Phosphorus is based on amount of phosphorus, the crop grown, and the amount of aluminum in your soil. And the potassium is based on crop grown and anticipated yield and amount of potassium. These recommendations all are pretty much based on the nutrients present in the soil. If you have any questions about this, there are lookup tables in the Vermont nutrient recommendations for field crops or something like that. I don't have the title correct. I think you guys know what I'm talking about. All right. I'm a little bit behind on my slides. I'm going to breeze through a bunch of this stuff, but I think it's pretty interesting. I do want to talk about nutrients for a moment. There's 3 different classes of nutrients that your plant needs for growth: macro elements, secondary elements, and micro elements. Macro elements and secondary elements are both needed abundantly by your crops, but in general, for the secondary elements, there's enough in there to supply your crop from the soil. These macro elements, N, P, and K, typically also need an abundance, but need additions. And I think one of the previous presenters also recognized that these are the elements provided from your soil, but plants also need oxygen, hydrogen, and carbon to grow as well. Okay. So I like to use this illustration to describe Liebig's law of the minimum. And basically what this is getting at is that if you have optimal levels of all your nutrients, except for one, that's going to be your most limiting factor. That's what's going to cause your crop quality or your crop yield to not be as great as it could. So if you've got enough nitrogen, phosphorus, and potassium, but not enough boron, that might stunt your growth. That might cause some nutrient deficiencies that would lower quality. Same is true of light or water, or sometimes even if these nutrients are in excess or water or light is in excess, that can also have an adverse effect. In general, if manures are being applied to fields, there's normally enough replacement of those micronutrients to not need to not need any fertility. But always refer to your soil test. And if you have any questions too, it's worthwhile. You can get a tissue test of your crop as well to see if there's any nutrient deficiencies. I just kind of wanted to draw attention to that plant deficiencies look different, or sorry, nutrient deficiencies on plants look different. And I like this because this just kind of shows on one theoretical plant that, you know, phosphates can leave, deficiency can leave leaves a little darker, nitrogen, so they're a little bit brighter, potassium a little bit yellower. And I'm going to lean into this a little bit more in this slide as well, because now we're just looking at corn. And I know that we have a lot of different types of crops out there, but this is an illustration that really, I think, kind of captures a lot of what these deficiencies can look like. So a healthy corn leaf, right? It's kind of shiny, it's bright green. If you see any phosphorus deficiency, that normally results in this purpling of the outer edge of the leaf. Nitrogen, you can see like that yellow midrib. I'm not going to go through each single one of these, but you know, you might also see like disease that looks like these little blotchy pieces, some chemical burn with this irregular browning on the tip. And then what I thought was interesting too is that phosphorus deficiency early in the season can also result in a shallow root system. And I've been thinking about this a lot too with the amount of flooding we've had in Vermont, that poor drainage also results in a shallow root system or just saturated soils, right? Because that water sitting here is filling up that pore space, meaning that there's not oxygen there, which means those roots can't live. So they die off and the roots aren't as deep, which means that they're not accessing any of those nutrients down there. I think one of the other interesting parts too is just looking at how ear tips can change in grain corn. I think this might be similar for other grains as well, but we've all seen a normal nice, fully developed, large ear of corn. But if fertility in general is low, we might have smaller ears. And potash deficiency can result in poorly filled tips. Phosphate deficiency can interfere with pollination and kernel fill. So you get a bit of an unfilled or underdeveloped kernel tip that's twisted. And then nitrogen deficiency can, at critical times throughout the growing season, can result in these smaller ears, unfilled kernels on the tip, and low protein content. I'm going to blaze through these a little bit too, just to say that nitrogen is important for chlorophyll formation and building amino acids. See, with more nitrogen, bigger crop, it's greener, our ears are bigger. What this looks like in forages, right, is that we can actually also impact the root structure a little bit too, in terms of the lack of nitrogen, like here in this tall fescue, creates a larger but finer root system, and it reduces tillering and causes chlorosis, this yellow bit on the end here. What it looks like in soy, soy can actually be a pretty high demanding nitrogen crop, and so we can see nitrogen deficiencies in bright yellow on the lower leaves. We're going to look at phosphorus deficiency and a little bit of potassium deficiency. So phosphorus is important for photosynthesis, respiration, energy storage, cell division, cell enlargement. And we see a similar issue with it impacting tillering and overall growth, and in corn, of course, like these purple margins. Potassium deficiency in crops, potassium regulates opening and closing of stomata, triggers activations enzymes for ATP production. And you can see it in soy, again, like this yellowing. So a lot of these deficiencies can result in similar looking diseases, or not disease, deficiency formation on leaves. And so it's really best to like consult your soil test, get a tissue analysis, or connect with a consultant to look at in-field in the season, what's going on, and make a correct diagnosis. Micronutrient sulfur can also be deficient in crops, and it is important in the formation of proteins. Some crops might need sulfur in higher amounts than others, and your soil test might be able to tell you that. I just wanted to give a shout out real quick to the 4 R's when we're talking about nutrient deficiency and nutrient need. It's best to time apply the 4 R's, applying the right rate from the right source at the right time. So the 4th one, I'm blanking on that in a moment, but I think folks here are pretty well versed with that. So, you know, for example, when you're growing corn, it's best not to put all your nitrogen down at the beginning, not only because it's so volatile, but that's not when your soil or your crop needs it the most. Can't help but put in there saying applying nutrients in excess can damage the crop, reduce farm profits, and can harm the environment. Best not to do that. Consult your soil test. And then also over-application can result in crop burn, uneven germination, slow growth, stem loss, and damaged roots. All right, one of my last public service announcements before we move on to another topic is to meet Vermont state standards. And I know that not everybody here is a farmer or consultant in Vermont, but it's required to take a soil test every 3 years. Tests should be taken around the same time of year. And the routine soil test really just measures the amount of fertility in a soil. It doesn't hit on some of those other soil health test indicators. So if you want to know more information, there's a nutrient recommendation for field crops in Vermont. And I think the agency would like me to point out that there's also, if you have any questions about required agricultural practices, there's the required agricultural practices rule for Vermont. All right, questions on this? I still have soil health tests to talk about, so I'm just going to throw it out there.
Just want to say, will you put in, I think the 4th R might be right placement.
Absolutely, thank you.
And then there was also just a quick discussion in the chat about what potash is, and it was clarified that it's a colloquial term for potassium. So just want to make sure everybody knew that. And I'll let you keep rolling because I do know how many slides you have left, so appreciate you.
All right, I'm going to talk about a few soil health tests, and I'm going to say that different labs use different tests and metrics. And I'm definitely not going to dive into these at depth, like for each one of these, as I did for the routine soil test. But I think it is important to say that in general, right, we talked about this for routine soil tests. For corn, we're going down to 12 inches, for forages 4 to 6, but for these soil health analyses, it's all 6 inches. We're not going down further than that. So the thing that I want to point out about the Haney soil test is that they do use different extracts. There's an H3A extract and a water extract. I just want to familiarize folks to what these might look like if you ever get one. And they also report things in different units, right? There's parts per millions, and they also transfer that to parts per acre, pounds per acre. And then also they do different fractions of what's in the soil, right? We talked a little bit about total phosphorus or reserve phosphorus versus plant available phosphorus. And then within that, what's organic versus inorganic. And that availability can change depending on different conditions. Also on the Haney soil health test, they do provide recommendations. This example didn't have one accompanied with it. I just wanted to show you there's this box for that. And this is interesting too, is that it also has a cover crop suggestion. I just thought that was the neatest thing. One thing that if you're getting super bored of listening to me talk, what you could look out for is trying to track one nutrient throughout all of these, because the soil health tests I'm about to show you are all taken from the same field. And they're not comparable at all because they're different labs and different tests. Okay, here's a Solvita soil health test. They also use different metrics in different units. They also have a ranking score. It has nutrient values present in soil expressed in parts per million. And it also has this overall fertility score and an overall soil health score. And then it also does provide recommendations for soil tests and has also a recommendation for soil for green manure and cover crop, which I thought was really neat. And then this is one I'm going to spend a little bit more time on. This is a cash test, and this is one that I'm most familiar with and has been used in a variety of research trials. And Alyssa White had also done a state of soil health in Vermont and used the cash test for that. So let's talk about this and what this looks like a little bit, and then we'll dive a little bit more into what it's like. So, oops. That animation is not working quite well, but in our first category, we've got a number of physical indicators, followed by biological indicators, and then the cash test also presents chemical indicators as well. Just in case you were bored and tracked organic matter, for example, what I did want to point into more specifics of the cash test is that if we compare for the same field organic matter results across all these tests, they're a little bit different. And I'm actually kind of a little bit surprised by that, because I think they all use pretty much the same measurements. But this is just another same standard operating procedure to measure them in the lab. But this is just to say, if you're not all tests, you can't necessarily compare different tests to each other. It's best to compare the same test from the same lab. Okay, so if you ever send a soil sample to Cornell for analysis, you might get a report back that looks like this. And so we're just going to walk through this rather quickly. And they do texture class analysis, which is really important. And part of that is because the ratings are adjusted based off of the soil texture. Again, we've got these 3 groups, and each one of these groups has these indicators, and then each one of the indicators has a value. It gives a rating based off the soil texture class. And then this overall quality score is the average of your ratings. If there's any constraints, it will give some ways of how that constrains. So we have our surface hardness. It's a really low rating. It constrains, rooting and water transmission. And I just have up here too this graph that I think actually Lauren made that I pulled from one of her presentations. That just kind of breaks down, what the score is, and then classifies it as it's functioning. So we have 5 different scores ranging from constraining to low to medium to high to very high. And basically what this is indicating is how much that might be reducing your soil health and impacting your crop yield. And I think about this kind of like Liebig's law of the minimum, that if your surface hardness is really constraining, it's probably going to impact your crop growth and the ability of your plants to pick up nutrients, even if those nutrients are there, right? Because it just isn't going to be able to create the roots at depth or as many roots because it's working real hard to do that. And so by addressing one of the constraints, you might actually be helping it access some of the other indicators or features you might have in abundance. But that, I'm not going to read all this, but I just wanted to say that one of the nice things about the cache report is that it will tell you for every indicator how it's processed in the lab, what your individual soil result is for that indicator, and then what that means, if it's in what category it's in, and then some management methods if it's in the low category to help alleviate that issue. I will say that pretty much all my slides that I have about the cache report are based off of the comprehensive assessment of soil health. Like all those images are pulled directly from there. So if you're interested in learning more, that manual is downloadable for free online. I think it might be included in the resources section. Okay, so what we're going to talk about here is soil texture class, and I'm just going to go really quickly about how these are analyzed in the lab. So just a little, the soil texture triangle, I think folks are pretty familiar with this, just in terms of, you know, the more sandy it is, more clay or more silt, and the different percentages you have falls into these different texture classes. There's a couple different ways to measure that. One is you put your soil into water, shake it up, and then let it fall over time. And generally your larger, heavier particles fall on the bottom. That's your sand, followed by your silt, followed by your clay. And then also in the field, you can do the soil texture class or texture by feel analysis. But how Cornell does it is this process where they, like most soils, when they send them to the lab, they dry it, they grind it, put it on, or they don't grind it. And then they put it on these different sieves to basically have the particles fall out over time, and they decant that water off. So what I think is really interesting and important to note is that texture class, like that percent sand, silt, and clay, is really based off of the particle size. And so when you're putting it into a sieve, whatever stays up, but the 2 millimeter might be like, and I don't know these exact measurements off the top of my head, but like that's all the sand, and then the next sieve, that's all the silt, and the smaller sieve at the bottom is all the clay. And just to speak a little bit now about available water capacity. Basically, this is talking a little bit about how much water your soil is able to hold, and that can really change depending on what your soil type is, right? So if you've got a clay soil, it has a higher level of ability to store water than your sandy soil. And that's part of the reason why these ratings are based off of the texture class, because it's an inherent soil property that does influence these indicators. And how this is measured is the soil gets put in these little cups. It gets put at 2 different pressures. It gets saturated with water, and then it gets put into this instrument at 2 different pressures. And I think it's the difference between the pressures of the water that's extracted that gives the available water capacity. Surface hardness is measured by compaction. We are out in the field doing this with a penetrometer, and it's measured in pounds per square inch, and that can really impact how difficult it is for the roots to pull down. You can also kind of get a feel for this in your field too. Like I think Fred mentioned like using a metal rod, like a coat hanger, to see where it gets stuck in your soil. You can also take a hole and you can see what's going on in your soil. So if you've got a bunch of roots, you're probably not very compacted. If you've got roots that go down like this to a certain point and then J out, a J root, that's because you've got a restrictive layer, and that might be because you've got a plow line or compaction right there. I would also say that one of the things I've experienced using a penetrometer in the field, and especially on one of our long-term trials, like got a continuous corn for the last 10 years, and then let's say perennial forage for 5 years. If I'm using my penetrometer to measure compaction in my continuous corn treatment, it goes in like that, you know, pretty much like all the way down to 18 inches, pretty easy. but I don't experience that in the perennial forage, and that's because the roots are, there's so many roots that's what's causing resistance. So when you're using a penetrometer, it's really important to know what that tip might be getting caught on. Is it roots? Is it rocks? And like, that's not necessarily an accurate portrayal of the level of compaction in your soil. All right, aggregate stability. So aggregate stability is a measure of the extent to which soil aggregates resist falling apart when unwetted and hit by raindrops. It's used, or it's measured with the Cornell rainfall simulator, and for the longest time I thought this was like the rainfall or infiltrometer or something like that. It's not. It's rainfall simulator. I think infiltrometer sounds a little better, but anyway. All right, so you got your, what you do here is or what they do in the lab is they break up the aggregates a little bit, they put them on a sieve, and then they put them underneath the rainfall simulator. And so you can't really see it very well, but it's this giant plastic thing that hangs up, and it's got like these little curlicue tubes that go from the inside of the plastic container to the outside, and that simulates the rainfall. And then there's a tube up here that you can move up and down that changes the pressure inside the chamber, which changes the amount of rainfall. So anyway, before they put it in the simulator, they weigh it dry, and then they put it in the simulator, and then what's left on top afterwards, as the aggregates break apart and fall through the sieve, they measure what's on top, and then that's the percent aggregate stability. The amount of aggregates that were able to stay on top after the simulated rainfall. I'm skipping over organic matter because I think we understand that well enough. There's the ACE soil protein index, and it's an indicator of the amount of protein-like substances that are present in the soil organic matter. ACE represents the large pool of organically bound nitrogen in the soil organic matter, which microbial activity can mineralize and make available for plant uptake. Protein content is well associated with overall soil health status because of its indicator, or it's an indication of biological and chemical soil health. So for this, basically the short version of the protocol is the proteins are extracted from a sieved, well-mixed, air-dried soil, and then they use a protocol developed from Wright and a couple other folks to put it in an extract, and then run it through a machine that gives a value for the amount of protein that it has. Soil respiration. So soil respiration is measured, it's a measurement of the metabolic activity of the soil microbial community. It is measured by capturing and quantifying carbon dioxide, CO2, released from a re-wetted sample of air-dried soil held in an airtight jar for 4 days, right? All right, so they dry their soil, and then they put this little CO2, or they re-wet it, they put this little CO2 trap on it, and then after, and they put a cap on, let it sit for 4 days, and then they read what the CO2 trap had to say. Active carbon, I think this one's really fun actually. So it's an indicator of the small portion of soil organic matter that can serve as a readily available food and energy source for the soil microbial community, thus helping to maintain a healthy soil food web. So what's done to measure this is, again, you got your air-dried soil, and they throw it in a solution of potassium permanganate. And the more carbon there is in the potassium permanganate, the less color it has, because it's kind of metabolizing that or using it up. So then that solution, after it's been sitting with the soil, gets put on a machine that reads basically the purple value, the amount of purple it has, and that gives it a value. Okay, and then I wanted to have a little bit of a shout out here about the difference, just thinking about what soil respiration and active carbon represent. And what we've noticed that soil respiration picks up cover crop differences more, and active carbon picks up manure differences better. And I think one way to think about this is that active carbon is kind of picking up more of a stable, stable conditions. It's because the manure itself is a digested form of the cover crop. So it's already producing something that is a little bit more stable in its addition versus a cover crop. All right, so I'm going to talk just a little bit, or just wanted to point out that in the Cornell Soil Health Manual, I think this is really helpful that for each one of their indicators, if there is a constraint, you can look at the short-term management and long-term management suggestions to address that issue or that constraint that's on your farm. One thing that was developed through UVM and NRCD and some crop consultants is a soil health action menu. I think this might be listed as a resource in the course, but basically this was developed as a way to think about soil health indicators and trying to engage the interest in a farmer of which indicator they'd like to address. So let's say they want to address nutrient cycling, that's high on their list. You can look over here to the right on the issue of interest and say, okay, we've got nutrient cycling on one of them. See, like low fertility might be an issue of interest. The goal is to increase fertility. Here are some potential practices that would help with that. And then here are different ways that you might assess any changes that occur before and after your practice change. And I think with that, I'm going to pause for questions for a moment. I think we're doing okay on time.
I think we are too. You just crushed that. I just want to say, I'll give you a second to catch your breath. We looked at a ton of cache tests this fall, and all of the surface and subsurface hardness across 7 different farms was incredibly high because we had gone out before it started raining in July, and it was hard soil. And so just making sure you take notes when you're out in the field with the penetrometer is really, really important about when you were there and what the conditions were. And one thing we had talked about is it isn't helpful to compare the hardness levels on different days, but it is helpful to compare across fields or even within a field on the same day. And so I just want to, that's something that took me a while to get my head wrapped around, because all the other numbers in theory you can compare kind of willy-nilly, but that hardness number is really, really, really weather dependent. So.
Yeah, Lauren, I appreciate you bringing that up. I know that's something that's really important to stress. And I would say, like, too, it might not just be a difference in environmental conditions that change throughout the season, but also management. Because a lot of freeze thaw can happen over the winter that might alleviate some compaction that's occurred by grazing. So what you might take in the fall might be quite a bit different than what you would take in the spring as well.
Yes. And then I just want to shout out, Mel just posted in the chat the soil health action menu that Lindsey just referenced. It's an incredible resource. Please print it and use it. And thank you so much for making it. There aren't any more questions right now. So if you want to hit your last couple slides, then we can just open up the floor at the end and ask anything else.
Awesome. And I guess I just would say too, on the soil health action menu, if you do end up using that and you have any feedback, like, that's one of the few things I can actually change in this world. So please let me know and we can make that happen. Oh yeah, so I don't have a ton of experience with this, but I did just want to note that there are a couple of other soil health assessments, visual in nature, and here's one that I'm a little bit familiar with, the NRCS Infield Soil Health Assessment, and that's, you go out and you look at some of these indicators, soil cover, residue breakdown, and rate them. You can also do a couple of like in-field tests, like the slump test or slake test. And then there's this other one that I became a little bit familiar with, which is the Michigan Soil Health Progress Report recording sheet, and I think it is similar in nature. Before I move on to any of my other slides, I think it's really important for me to mention that, you know, what I've presented are some of the tests or assessments that I'm familiar with, but There are other tests and assessments that are also valid and really useful. I just don't have a lot of familiarity with them. So for example, there's a wealth of knowledge on traditional ways of assessing soil health and plant health, and I'm just not particularly familiar with those, but they're valid, and I would encourage folks to seek out and use those resources as well. I just didn't feel like it was appropriate for me to speak on something I don't know much about, but did want to acknowledge that. So I'm going to talk a little bit about biological tests, starting with the ecoplate. So in general, the ecoplate, you've got 31 wells, 31 substrates that are repeated 3 times. And what these are is that they represent different carbon sources, and so and there's a bioreactive dye on them. That's what you see on the right. And so this will spit out some information on microbial populations and microbial diversity. And so one of my colleagues had us take samples a few years ago on one of our trials every month, May, June, and July, and August, in these different treatments. And there's a bunch of different treatments, but what I really want to focus on right now is this gray bar at the top, or line, which represents perennial forage. And then looking at this bottom, which is continuous corn. So this is corn without cover crop and in no-till conditions. And although the microbial community populations change over the season in pretty much all of these different systems, like they increase, so that's important to note, but also we can see that the populations are lower in the continuous corn throughout the season. And that's to be expected, right? There's not as many living nutrients there. Sorry, I meant to say roots. There aren't as many roots there, living cover, which contributes to the food sources of the microbial communities. And so one of the other things then looking at the data is that we can also look at diversity, and that's what this graph shows. And it's really similar with microbial populations and microbial diversity. We also saw this with pH changes, is that you might have more populations, and that also coincides with more diversity. And again, we see that our perennial forage, over time, the diversity pretty much increases, and it's much higher than our continuous corn. And I'm going to talk a little bit here about PLFAs. This is not something I know a ton about, but I just wanted to touch on it. The PLFA stands for phospholipid fatty acids. These tests serve as a very good indicator of soil microbial communities, and they're measured with a gas chromatograph machine that can measure the phospholipid fatty acid content of a particular soil sample. Sorry about that. And it can provide a real-time snapshot of the soil microbial community. It indicates the amount of microbial biomass and proportions of microbial types, such as mycorrhizal fungi, gram-positive fungi, gram-negative fungi, and a number of other types. I think what's interesting to note here is that this was just something that I pulled from Ohio State University newsletter, but this is their analysis of a no-till cover crop situation versus a tillage no cover crop situation, in which we have more bacteria and also more fungus in a system that has no-till with cover crop, which makes a lot of sense, than in a system that has more, or that is tilled and has no cover crop. Environmental conditions such as pH, temperature, and moisture can also impact these microbial communities, as well as organic matter, crop rotation, herbicide and pesticide applications. And this is what a PLFA test can look like. I mentioned some of these functional groups that are measured. And I'll be honest and I'll say that I'm really, really interested in this topic, but I know very little about each one of these pieces. I think this is something that our previous presenters touched on, were like the protozoa and the mycorrhizae and the saprophytic fungi. All right. And beyond. So the beyond part of this is genetic testing from microbial communities. And I think that this is pretty fascinating. I think there's the PLFA and gene sequencing can be a little bit costly. The eco plates, I think, were like $15-20, so that's a little bit more affordable. But what's really cool about quantifying soil microbial genes is that it helps us understand the diversity of microbes in our soil, and that they play an important role in maintaining the health of our soil by recycling nutrients, by creating soil structures and humus. And then through this gene analysis, right, we're able to understand soil processes better, and gain a better understanding of plant microbe interactions and sustain ecological balance, critical functions to ecosystems, and think about how we can conserve microbial diversity in agriculture. So there's this amplicon sequencing, which uses the 16S rRNA gene, and they're using this gene because it's conserved in most bacteria, so they're able to figure the which bacteria are out using this gene. And then there's this whole other complicated thing that's like much more expensive, the metagenomic genomic sequencing. And this is a cultivation independent molecular approach to explore the diversity of soil microbial communities, but it gives us a lot more information than the amplicon sequencing, and is also comparably a lot more expensive. I'm not expecting anybody to do use any of these tests anytime soon. I just think that this is kind of on the forefront of what our technology is now allowing us to do, and maybe to keep our eyes open for it in the future and what it might be able to tell us about ecosystem service and microbial processes. And with that, I will stop.
Thanks, Lindsay. Incredible job. Got a question from Mel. Maybe this can't be answered, but do you see biological tests or other soil health tests becoming more important in a regulatory sense, similar to the way routine soil tests are used for nutrient management?
I don't know about regulatory. I could see them being used more so for like a pay for ecosystem services situation. If different companies are interested in that, and yeah, maybe as indicators for regenerative agriculture down the pike.
So thanks. There's not any more questions right now, but I know this group and I'm sure there's some floating around. So if you do have questions, please feel free to come off mute or put them into the chat. One thing to stay busy, you talked about how to collect a routine soil health sample. I don't know if you wanted to comment on how to collect a cache soil sample, because that is a little different.
Yes. So I can't remember how many soil samples you need to take. I think it might be 5 for a cache soil health test. So it's 5 locations in the field. At each location, you take 2 6-inch depth soil samples. And what I kind of try to aim for is that they're 6 inches, but then all the way down that 6 inches, you want to make sure that you have the same width of the face. So I'm like, I dig like a hole, I put my trowel in, I pop it up, and then I try to, because often when you go into the soil and you pop it up, you might have more at the top here than at the bottom. So I want to make sure that's even. If this is my trowel, this is my soil layer, I want to make sure that this is all even. So you do that twice in each of your 5 locations. And with each one of those soil samples you're taking, you're also optionally taking a compaction measurement with a penetrometer if you want to get a sense of surface or subsurface compaction.
And obviously the cache test has an aggregate stability indicator that a routine soil health test doesn't have. And so I know when we were out there collecting, we made sure not to like crunch up our soil, I guess, so that you still had aggregates in place, I guess, when we sent them to the lab. I don't know if you want to speak to that a little bit.
I will say I am not particularly gentle with my soils in that.
Fair enough.
And keep this in mind, right? Like, you know, so I take my soil samples, right, and I might homogenize them first by like banging them up around the bucket a little bit. And in some soils too, there's a lot of compaction, or it's dry and they're hard, and you want to send a homogenized soil sample and not 2 pounds, but whatever they're asking for. And to homogenize it, you're going to need to break it up a little bit and mix it up too. And keep in mind too that especially for aggregate stability, they're not grinding the soils like they are for a routine soil test, but they are breaking them up some, because, you know, if you've got a soil with real good till or real good aggregation, you might get a clump that's like that big, but if you press your finger on it, it's gonna break a little bit. And that's okay, because we want to have something that's a little bit uniform in size. So yeah, you don't want to like squish and compact and be absolutely rough, but I mean, soil's pretty tough. You don't need to be overly gentle with it, I guess. You know, yeah, I guess that's what I say about that. Yeah, I really squish those bags in there when I ship them out in a box. I'm trying to get as many as I can in one of those flat rate shipping boxes. But I'm not also like sitting there being like doing any of this business, you know.
Very fair. I'm wondering if you would be willing to take your screen share down, and so people can see each other if folks do have questions for Lindsey.
I'll start. Lindsey, thank you
Hello.
very much. Great job as usual. There's always something to learn, just even if you feel like you know something, sometimes you don't know much of anything at all. So thank you for that. The state of soil health in Vermont, that project, can you just go over it quickly and just kind of tell us what you think it means?
Oh. I think one of the biggest things that we learned from it is that our soils in Vermont are quite excellent. And so I think that if we were going to use the soil health test from Cornell, and we're looking at overall soil health scores, that we might want to make a broader range for our categories. Because so many of our soils were in the high and very high categories, which is excellent. Like that's amazing and really important and valuable to acknowledge. But I think from a change perspective, if I had a farm and my test results said I was doing well or really well, I'd have really little incentive to make changes, even though some changes could result in better soil health. So I think that was one thing that we pulled apart, is that in comparison to our neighboring regions, we're doing really well. And I think a really big part of that is because on so many of our fields, we are incorporating manure, and that is a significant addition of organic matter, and is I think so important when we're talking about our food system and talking about having a nutrient cycling process on our farm. Like, I think animal integration is just incredibly important. I don't think that really answered all of your question, but we could include the state of the soil health report in in the resources.
Oh, I appreciate that. I just want to hear how you processed it right now. Thank you. Very good.
Hey, Lindsey, one more question I was just thinking of, or a point to comment on. I know with the routine soil health tests, we're typically suggested to do those in the fall, at least 2 weeks after the last spreading of manure on a field, whereas the cache test is actually recommended to be done in the spring. I didn't know if you wanted to speak to that a little bit.
Yeah, I think one thing that's important to think about when we're talking about the routine soil health test versus the cache soil health test is that the cache soil health test also measures biology. And when we're thinking about chemical indicators, in general, I wouldn't expect there to be too much of a difference between a fall and a spring, but also the spring is super busy for the farming community, and it's one more thing to add out there. And oftentimes there's like a wider window to take soil samples in the fall, and it's a nice, steady, consistent time to take that soil sample. I think one thing I think about with the soil health test and taking it in the spring is that's when like the microbes are just starting to like wake up from their wintertime slumber, and so that can be a really great time to capture that. I think it's also important to notice, and I didn't say this in my presentation, but the soil health test doesn't capture everything either. And I think I've seen this because a part of that state of the soil health or other projects we've been on, we'll get a soil health test back. And like, I remember in particular, there was one that was great. It was just like the best of the 30 farms we had taken in like May one year. And I was talking to Heather about it, and I was like, oh, it's from a field you took a sample on. And she was like, that field looked awful. Like, how could that have been? You know, compared to like the other fields that she had taken samples on and the management methods that she knew. So I think in particular, and because we just saw that ecoplate example with fluctuations in microbial populations and communities over a season, that those field conditions can impact those microbial processes that impact the soil health test in a way that it doesn't quite impact a routine soil test. Yeah, I think that's what I got to say on that.
Makes sense. I've got a question, percentage wise, how many farms are taking soil health tests? How many of those, I'm gonna guess, how many are taking soil health tests versus routine soil tests? How many farms and how many fields on each farm? Sorry, I got confused.
So for Vermont, I was going to say, I hope every farm is taking routine soil health tests because it's a requirement and it gives you really good information. I'm not going to lean into that too much. And I also want to say that I really, really enjoy working with farmers, and I wish that I did it more. And that's just a preface to say that my sample size of farms that I work with in Vermont are really, really tiny. So I don't think I can say here's a percentage of farms that use soil health tests. But I will say that with the farms that we partner with on a variety of projects, they often have soil health samples taken on their farm. But that's not necessarily something that farmers are opting in for. And it's like $100 a test if you want all that stuff. And there are other ways to gauge the health of your soil without paying that much. What I like about the soil health test is it gives me a value that I can work with and pump stats and graphs out of in a way that a visual assessment wouldn't for me in the work that I need to do. And I think it also can be helpful because you can see those changes, but sometimes it's also nice to have a value that goes with them. You know, like from a personal example, I gained all that weight over Christmas, and I can see the change, but I also like the scale to tell me that I'm making progress. You know, that's kind of one analogy. Welcome to the new year, everybody. Willie, I saw you came on mute for a moment. I don't know if you wanted to jump in.
Oh, I think it's a very small number, right? But one of the things I'd like to say is that kind of like as we've evolved in our understanding of use of cover crops over the last decade in particular, where we kind of had just like, let's just throw anything out there or something out there and hope it does something. And we've become much more understanding and refined and be able to, one of the biggest question we ask is, what do you want the cover crop to do for you? And I think that's what we want to ask a soil health test. What is it we want it to tell us? So we have to be able to have a good sense of what it is we're working with, what our goals are, what kind of soils we have, what is it where's that weakness in the system perhaps that we're trying to remedy the most, and what maybe a test. And the one test that I would say is everybody should just do for themselves no matter what is soil structure is something anybody can do. You can just go out and do it. I mean, if you can tell soil structure by putting the shovel in the soil and plopping it up and doing some time with it, right? So, but I think we get better at soil health testing by asking, what do we want to know? And as we ask that question, we don't have to do all of it. We can pick and choose which analyses we want at different times.
Thank
Willie,
you.
since you mentioned cover crops, I gotta give a shout out to this book, the Managing Cover Crops Sustainably book. I know it looks backward for you guys if you guys don't know about it. It's really great. One of the things I like about it is that it gives an in-depth review of a lot of different cover crops, but in the middle of it, it also has this really awesome table that breaks down the superpower of each of the cover crops and maybe what some of the limitations are. So like got like little tables like this. That doesn't really push. I know that's all fuzzy, but potential disadvantages and planting depth, the potential advantages, performances and roles. It's all like quick little snapshot of everything. That's super fuzzy. Not working. Okay. Anyway, that's why you put little pictures in your PowerPoint. Demonstrate that. But anyway, it's a great book, also for free online, published by SARE, same folks who published the Billion Soils and Better Crops.
Wonderful. Thank you so much, Lindsey. We asked a lot out of you today, and I think you really delivered. I know I'm going to be rewatching this several times this year as I'm writing new NMPs and working with farmers on their soil health. I actually think this could be a really incredible tool to share with farmers too, who are really interested in their own things and want to understand all these different indicators. So thank you for this incredible resource.
Yeah, well, thank you for having me. It was fun to do.
Wonderful. And then just for the last minute of class, just want to get prepared for folks for next class. It'll be next Tuesday on the 16th from 2 to 4 p.m. again on Zoom. It'll be Heather Darby talking about organic matter. If you are able to fill out the evaluation form, I hope you heard Lindsey say several times that she was asked to speak about a number of different things. And those are things that came out of the evaluation form and lingering questions. So please do continue filling that out. And go find a soil health test or a routine soil test in your office and look at it with maybe a different set of eyes and think about how you can explain it to a farmer. As always, if you haven't yet, please set up your campus account and look at all of these incredible resources that Lindsey has sent over for us. As well as please read chapter 9 of our textbook for next week, Managing for High Quality Soils and Focusing on Organic Matter Management. If you have any questions at any point in time, please reach out. And I hope everyone has a great rest of your day. Thank you all for coming.